10 years ago, enterprise software was built like a single, rigid stone structure. Today, that architecture has shattered into small, independent modular units that can be updated and scaled without affecting the rest of the system. Most of these legacy monolithic applications were sunset or migrated years ago. Running a business on a static virtual machine is no longer the standard for new development. In modern tech hubs like Seattle, the job market has moved on. For today's engineers, managing modular, containerized workloads is a baseline requirement for entry. This chart illustrates that shift. Approximately 75% of all net new compute workloads are now deployed using Kubernetes, rather than traditional server models. This scale makes manual configuration, or ClickOps, operationally impossible. Clicking through a web console to manage independent services introduces human error and configuration drift. Instead, cloud engineering now relies on command line interfaces and declarative code to define exactly how an environment should look before it is ever built. We'll trace this lifecycle end to end, launching an ephemeral cloud shell, wrapping it in Docker, and deploying to a Kubernetes cluster. Building this pipeline allows a team to move away from manual server maintenance and toward a system of predictable, automated deployments. The process starts by bypassing the local laptop environment entirely to launch a GCP Cloud Shell. The first command is strictly administrative. You must authenticate your account and set the specific project ID to ensure your work is walled off within the correct billing and resource boundaries. This shell isn't a local terminal. It's a temporary container inside Google's infrastructure, pre-configured with specific cloud tools. Functioning as a bastion host, it provides a secure environment that removes the need to spend weeks configuring local drivers on a personal machine. Once the environment is ready, we use Docker to package the application code for deployment. A Docker container wraps the code in every library and runtime it needs, creating a standardized replica. This ensures parity across test servers and production clusters. Carrying its own environment makes it highly portable, allowing organizations to move workloads between cloud providers without rewriting logic. Executing a simple docker build command in the shell finalizes this package into a static image. This solves the common failure where code runs in development but crashes in production due to subtle differences in server configurations. With the image built, it must be moved out of the temporary cloud shell and into long-term secure storage. You must first tag the image with a specific path that includes US West 1 to tell the cloud exactly where this image belongs. The destination is the artifact registry, a private internal vault for an organization's containers, acting as a secure alternative to public repositories. Inside, automated vulnerability scans check the container's libraries for known security risks before it is ever deployed. However, moving an image into this vault requires navigating GCP's Identity and Access Management, or IAM. By default, the cloud is locked. Every API is disabled. Every access request is denied until explicit permission is granted. To push the image, you must assign the artifact registry writer and administrator roles to your account, providing the explicit authorization the system requires. In an enterprise environment, your code is only as useful as your ability to navigate these security and permission layers. Once the image is in the registry, you must decide which compute model fits the workload's specific requirements. The first option is Cloud Run Functions. This is a serverless model designed for short, single-purpose tasks that don't need to run continuously. This event-driven model means if a user uploads a file to a bucket, that event triggers the function to wake up, process data, and output. Because the function only exists for that task, it scales to 0 when idle, charging only for exact seconds used. For workloads that are more complex and need to be constantly available, we use the Google Kubernetes Engine, or GKE. GKE provides a cluster environment for long-running microservices that need to handle thousands of requests simultaneously. Inside the cluster, services are constantly communicating, passing API requests back and forth between different pods to complete complex transactions. Within GKE, there are two primary ways to manage the infrastructure: Standard and Autopilot. GKE Standard gives total control over the underlying virtual machines, but it requires the engineer to manually manage node scaling and security updates. GKE Autopilot abstracts that complexity. Google manages the underlying nodes for you, allowing you to focus entirely on the application rather than the hardware. Choosing between a serverless trigger and a managed cluster is what defines the cost and performance of a modern cloud application. We have now mapped a complete CI/CD pipeline. From writing code in the Cloud Shell and packaging it with Docker, to securing it in the registry and deploying it to GKE, every step is linked. But to run this at an enterprise scale, we cannot rely on entering these commands manually, one by one. A manual process is difficult to document, hard to replicate, and impossible to scale across hundreds of different projects. This is where infrastructure as code, or IaaC, becomes necessary. With tools like Terraform, we define this entire architectural map as declarative text files. Since the infrastructure is defined as code, it can be version controlled in a repository, allowing an engineer to rebuild an entire cloud environment automatically in minutes. Relying on manual UI clicks is no longer viable in an industry that requires this level of speed and precision. Mastering this code-to-cluster pipeline is the transition point from simply operating cloud tools to architecting automated enterprise-scale systems.